Okay, we're here on the second half of Freefall, working with projectiles, heading for projectiles. Miss Edie Water is going to be platform diving here in Ringling Brothers Circus. The platform is 20 meters high, and she jumps into a small bucket of water. Now, it asks us to state the acceleration as she is falling from the platform. Now, the acceleration is going to be 9.8 meters per second, which we can round to 10 in many cases, toward the ground. So it's an acceleration, it has to have a direction, it's going to be downward. Now the assumption I have to make, I have to assume she's in free fall. And that means I have to assume that no other forces except gravity act upon her. So I am neglecting air resistance. I'm assuming it's small enough that it's not going to have an impact. That's not really true. As she speeds up, the air resistance will increase. She'll be less and less in free fall. The acceleration will become smaller and smaller from 9.8. But it's a okay assumption if we're just trying to get a general sense of the motion of her as she falls. Part B, the velocity after the first half second is represented by an arrow. They're asking us to draw the arrows afterward. So what we should see is an increase in her velocity. So in the next step, this arrow also should be downward. The force of gravity is straight down, but it should be longer. And then with each successive situation, she is increasing her speed. Now, it's really important to understand that the acceleration is what's constant, but acceleration is not her motion, it is the rate of change of her velocity. It's telling us how much faster or slower she's going to get. So her rate of acceleration is roughly 10 meters per second for every second that she falls. So if the pictures were taken at 1 second intervals, she would have gained 10 meters per second every second or every picture. Okay. Now to fill in the tables below, therefore, if we're looking for the velocity, if we're looking for V or VF, the final velocity or the velocity at any time period, it's going to be the acceleration rate times the time. She's starting at rest. We would have to add to that any initial velocity, but she's starting at rest, so it's just A times T. And again, A for free fall is G. So it's just going to be 10 meters per second for every second multiplied by the time in seconds. So 10 times 0.5 is 5. 10 times 1 is 10. 10 times 1.5 is 15. And 10 times 2 is 20. So you see there's a constant, consistent increase in the value of her velocity, the magnitude. Now the distance falling will not be consistent. It's going to, as she speeds up, she's going to fall further in each little interval of time. The distance that she's going to fall will be based on S would be 1/2 of GT squared. So it's based on her time squared. Now again, there would be a U times T factor or initial velocity times T factor, but she's starting from rest, so we don't need that part. That means 1/2 of 10, which is 5 meters per second for every second, times T squared. Now, T squared is going to be second squared. That's going to cancel both of these, and we're going to be left with meters. Here, the seconds canceled out this one, and we're left with meters per second. So 5 times 1 is, 1 squared is 1. 5 times 1 is 5 meters here. And 2 squared is 4. 4 times 5 is 20 here. 0.5 seconds, we're talking about 0.5 squared is 0.25. So 0.25 times 5 would give us a 1.25, 1.3 meters roughly. And 1.5 squared is 2.25, and we're going to multiply that by 15. Multiply that by 5, sorry, and we get 11.3 roughly. So you can see these numbers are not going up as consistently. They're not going by an equal amount each time. They're getting larger and larger and larger as they fall, and again, that's because they are faster and faster and faster as they move. Now, HT here stands for height. So she started at 20. 20 take away 1.3, she'd be at 18.7 meters at that point. Okay. Then we'd have to take away 20 minus 5. At this point, she'd be down to 15. 20 minus 11.3 is going to be 8.7. And of course, 20 minus 20, that's when she's reached the ground. Okay, so height is how far above the ground you are. Distance fallen is how far you have actually come down as you fall. They are not the same thing, but they do match up based on where you started from. Okay, so if I'm showing the work for any one of my rows, say the 1 second, that's the easiest one to do. Again, the velocity would be v is going to be at, is going to be gt, is going to be 10 meters per second times 1 second. Seconds cancel out, and I'm left with 10 meters per second. For the distance fallen, that's going to be 1/2 at squared, which is 1/2 of g, which is 5 meters per second times t squared. 1 squared is still 1, so I'm going to have 5 meters per second times 1 second squared. Second squared will cancel out with these two, and we're left with 5 meters. If you want to know your current height, take your original height, and we're going to subtract away how far we've fallen, and we're at 15 meters. Okay, Michael Jordan was said to have a hang time of 3 seconds in the commercial anyway. We're going to try to figure out what height that meant he would be able to leap to if he had a hang time of 3 seconds. Now, if he has a hang time of 3 seconds, that means it takes 3 seconds to go up, 1.5 seconds to go up, and 1.5 seconds to fall. One nice thing about this jumping up and down free fall, we do have a lot of symmetry. So the time it takes to go to the top will be equal to the time it takes to come back down. Now, if we're looking for how high off the ground he's going to get, the distance he would travel is going to be equal to ut plus 1/2 g in this case, because we're talking about acceleration due to gravity, t squared. Now, that's a quadratic equation. I could solve it for the whole trip as a quadratic equation, or I could simplify my situation by just saying I'm going to look at the second half, because the distance he falls is the same as the distance he went up. Now, at the top, he's going to have to stop. That's going to be his maximum height. If I say that I know he reached the peak when he stops, then my u for the fall part, the falling part of the motion, is actually going to be 0. So the distance he will fall is equal to, this part's going to be 0, 1/2 of g, which again is 5 meters per second, times the time, 1.5 seconds, squared. Now, 1.5 squared is 2.25. We're going to multiply that by 5. And we'll get 11.25 meters. So if he actually could have a hang time of 3 seconds when he leaped, he would go up 11.25 meters, and he would come down 11.25 meters. Now that's not feet, that's meters. That's well over 30 feet. And the rim is only 10 feet off the ground. So it's very, very unlikely that he has a 3 second hang time. A 4.5 second hang time is a good hang time on a NFL punt. So 3 seconds is a very, very, very long hang time. His hang time would be a lot less. It is a commercial, They're trying to make the point that their shoes are great, but 3 seconds is a clear exaggeration for how high and how much time he could spend in the air. Okay, so that's some of the basics. Again, to reiterate, free fall does not mean falling. Michael Jordan was in free fall when he was leaping up as well as the time he was coming down. It means that only the force of gravity is acting upon you. We're neglecting air resistance and other forces. We're going to have the acceleration, therefore, of 9.8 meters per second toward the ground. Often we'll round that off to 10 for simplicity's sake, but it gives us the acceleration right away. Again, we're going to want to use a lot of symmetrical situations. We'll see that as we move forward in the projectiles. And that's it for this episode.